I usually work on dynamics and apply to astrophysical problems, but this time I wanted to present something that is more like more broad than, let's say, the specific topic of astrophysical interpretation of gravitational wave signals, and talk something that is more fundamental in the more, let's say, common ground in physics. So yes, the three-body problem, so the gravitational three-body problem has a long history and can be applied to several modern problems in astrophysics, including exoplanetary architectures, triples and multiple systems, star cluster evolution, and of course the origin of gravitational wave sources. And I'll be talking a little bit about it maybe later. But for now, we can, let's say, forget all the astrophysical context and let's go back to the basics. And if you look at it at face value, that the three-body problem is one of the most ancient problem in physics. It was formulated by Newton. After solving the two-body problem, he tried to think about what was the possible solution of the three-body problem. Many other famous mathematicians like Lagrange or Laplace or Poincaré worked on this problem, either from the theoretical point of view or to apply, for example, to the lunar problem, the precession of the lunar axis, of the moon axis, apsidal lines around the Earth, as influenced by the gravitational force of the sun. So three-body problem, the Earth, the moon, and the sun. And eventually, Poincaré demonstrated in 1892 that it's not integrable, that you cannot have a solutions to the three-body problem, just like we have for the two-body problem that is purely analytical and beautiful, like as Newton found. But we can solve it on a statistical sense. And the discovery of Poincaré actually got him a prize from the King of Sweden back at the time for one of the greatest discovery in mathematical physics at the time, and paved the way to a branch of mathematics that include chaos theory, bifurcation theory, and camp theory. So there are two kinds of triple systems. You have hierarchical triples, just like the moon, the Earth, or let's say the closest stars to the sun, which are Alpha Centauri. They're actually in a triple system, where two stars are in a binary and are orbited by another body. But there is another kind of triple system where there is no precise hierarchy and everything can appear very chaotic. And these are non-hierarchical triples. We can also call them three-body encounters. They're not quite stable, and just to give a better astrophysical context, they should exist in nature, and especially in very dense stellar environments like globular clusters or open clusters. And at the core of these clusters, these clusters evolve via gravitational interactions, long-range interactions that bring the dense core of this cluster to increase in density, stellar density, which means you have a very high chance for three stars to meet together or three black holes to meet together. And if you don't have any binaries at the beginning, you can actually form new binaries and from the casual encounter of three stars. Or you can, if you already have a binary, you can tighten them up and make the separation of these two binaries get even shorter and shorter until, if they're star, they might merge. You can have like exotic phenomena or things that you can observe like blue stragglers, or you can have gravitational wave transients. If the two black holes are close enough, they are going to merge. Yeah, gravitational wave radiation. So how does it look like? Three-body encounter. You can see in this three-body simulation that I've run. You cannot see, unfortunately, this is hiding the time, but it's not big issue. This kind of three-body encounter is modeled via simulations. This is a particular simulation. No. I would like to say I did stop the simulation when the two particles are very close for dramatic effect, but it's actually a byproduct of the integration method, in which actually this is called regularization, and the system is integrated in a different Hamiltonian, and the time is also a variable that is integrated in a fictional time. But this allows despite sometimes the trajectory may seem a bit polygonal, so quite sparse points in times, it allows for extreme accuracy of the integration, and one can model very well even very close passages. So you see that it's quite difficult to understand what's going on in this picture, and but we can make a few basic observations. First, we have some time in which the three particles basically spend most of the time in the same regional space. Here, not. Here you have a brief excursion, as we call them. Basically, there is a temporary binary that is formed. There is a single who briefly recoils, and then this has to end, and they meet again until the very last end. So, okay, this is again, we call it scramble or democratic interaction. This is an excursion, and then here we have the end of the simulation. So we can, it's possible to demonstrate mathematically that this kind of configuration can never end up in a stable triple system. So you cannot form a hierarchical triple from this configuration, but what you obtain at the end is always a final binary and a single that are unbound with respect to each other, are on hyperbolic orbits. And these are basically these two observations. So every triple system decays into a binary on a single pair. Of course, I'm talking about non-hierarchical, and we should ignore braids, which is another topic for another day. And the succession, so this triple system, we can subdivide it into microstates. So democratic interactions and excursions, where you have a temporary, unstable hierarchical triple, if you want to call it like this.
The figure of 8 is non-hierarchical and stable.
It's a braid, that's why. Yeah, that's why. Let's ignore braids. Yeah, but yes, but yeah, they're very interesting. It's highly unlikely there can be in nature, formed in nature. And so a way to solve this problem, of course, what you've seen is an approximate numerical solution of a single iteration of a very specific three-body problem, but of course it's not a general solution. And we know that it's impossible to find a general solution, but back in the 70s, and actually it was started here in this very university by Monaghan, the introduction of statistical escape theory. So an idea, a way to solve this problem statistically and kind of give up solving each and having a specific solution of the three-body problem for each configuration, but just considering the problem from a statistical point of view. And the idea is to map an ensemble of initial states, which means only the global conserved quantities, so angular momentum and energy, to an ensemble of final states. Final states, as I told you, they are the, say, major axis eccentricity of the binary, the escape velocity between the binary and the single, for example, maybe the orientation, if there is a preferential direction, which is given by the total angular momentum, and so on. So the key idea is that we can leverage chaos to motivate this statistical theory, because chaos erases effectively any memory of initial conditions, so specific velocities and positions, but global conserved quantities. And once the system explores uniformly all the accessible phase space as defined in canonical coordinates, so you can basically imagine that the system uniformly explores all the available space, and chaos erases all specific information. We can simply expect that as the system explores the available phase space just by due to the chaos of the interaction, at some point it will have to decay. It will have to decay into a binary, into a single. And so we can simply find out what is the accessible phase space when the binary and the single decay, and sample from it as if it was a, say, a probability distribution. And this is the key idea of the statistical escape theories of the three-body problem. It's also called the ergodic principle, because we assume that the three-body problem is uniformly exploring in time all the accessible space, but only in time. But since this happens, we think uniformly, we can simply sample from the phase space. So we go from time average to ensemble average. And this is very well-known principle. It's even used in the data analysis of gravitational waves. So this is the beauty of this formula is that one can write in closed form this the phase space volume in terms of canonical coordinates. So canonical coordinates means this the momentum and position of the single, the internal momentum and position of the binary. And of course, we have to impose some constraints. Two constraints are given by energy and angular momentum conservation. So when the system disintegrates, so the total sum of the angular momenta of the binary and the single needs to be equal to the total angular momentum. Same for the energy. So for the energy, binary energy plus single energy needs to be equal to the total energy of the system. And other constraints come from causality. So we need to assume that this single comes from the binary, because if this single came from that direction, we know it was not ejected from an interaction. So causality is the constraint that makes our phase space finite instead of infinite, because it would explode, of course. There is, if you were to integrate the phase space without any constraint of causality, this integral would just go to infinity. And so it's possible to find a closed form expression of this. We can marginalize this over, say, Majoraxian and eccentricity, and we can have outcome probabilities, outcome distributions. So given total energy, angular momentum, and masses, here is what you expect to see. So if we repeat this experiment many times, and we always observe what is the final, say, major axis of the binary that has decayed, what is its eccentricity, this is what we expect to see. And we can do this experiment. We can have the theories, we have numerical experiments, and we can compare the two and see how good is this. And it is quite good, for the most part. And what I want to show today is that it's good as long as the three-body problem is chaotic. But by chaotic, it's best to, let's say, go also back to the basics. And I've talked about chaos, but I never specify what it is. We always have intuitive ideas. But in more practical term or mathematical term, is the exponential divergence of neighboring trajectories in phase space. Which means if we take a system, evolution, a dynamical system, if you want, if we perturb slightly the initial conditions, and then we evolve it again, and we measure the distance in phase space between these two solutions, we'll see that if the system is chaotic, these two solutions need to be divergent. So a small change in initial condition leads to a completely different final outcome. And to see that the three-body problem is chaotic, it's possible to do a very simple experiment without going into details, without measuring the Lyapunov timescale or the Lyapunov exponent. And we can do a simple three-body experiment, just like the one I showed you in the video earlier. So we take a binary with a certain, say, major axis. We take a single. Center of mass is at rest. Also, the single is at rest, separated. And we have only two free parameters in this configuration. One is the binary phase, and the other one is the inclination of this binary with respect to the line of the encounter. And if we evolve this system, the center of mass of the binary and the single will attract each other, and we will have a chaotic encounter, just like you've seen before. But in this way, we have two free parameters, an angle that goes from 0 and 2 pi, and a phase that goes from 0 and 2 pi or 360. So what you're going to see here is a million simulations in this phase space, initial phase space. On the x-axis, the binary phase. On the y-axis, the binary inclination. Each dot is a single interaction. And the color of the dot is the identity of the body that escaped. In this case, I chose to have slightly unequal masses. So you see, for example, if there is a symmetry between these two features that emerge, there is an asymmetry. And if I were to choose, for example, equal masses, this should become kind of equal. But you see that here we have quite a different feature. So here we have quite a sea of chaos. So each neighboring point seems to have a different color. While here, every color has this, we have a swath of a region of uniform colors. Which means if we take an interaction here, I change the phase by a very large amount, you always have the same final outcome. So here, the three-body problem is not chaotic. Here is not. Here is not. Here is not. Is it here? Maybe. Maybe. And you see also this correlation in the lifetime of the system. So how long does it take for the triple system to decay to a binary and a single? What you see here color-coded is the breakup time of the lifetime of the system. You see there is one-to-one correlation between very short lifetimes and regions that are extremely uniform, which they have always the same outcome of the interaction. So you see, there is not even need to look for the Lyapunov time of the system. There is always the same macroscopic outcome in this case. And in this region, the three-body problem is not chaotic. And also the three-body problem is very short. It's very short-lived. So this black region in phase space is it means the three-body problem just breaks immediately. We call it a prompt interaction. There is no time for the system to interact. There is no time for chaos to arise, and so we always have we have very little sensitivity to the initial conditions. Okay, so far is everything all right? No questions?
The binary is circular, right?
The binary is circular, yes.
It's really important because if you're not phased.
Yeah, otherwise, yes. It's a 2 degrees of freedom artificially, of course, there should be. Yeah, please.
In the plot where you have the big green and red regions, why are they still speckly? The outcomes are the same.
What, they're still?
They still look speckled, but it's not just a big green region. As in, I don't understand the plot.
The white dots.
Yeah.
The white dot is just the background of the. So you have a white background and you have dots in this background. Yeah, because they're not pixels; they're really dots. Okay. Yeah. So it's basically there are dots, a million dots here. Yeah.
So in the next one, do you understand why the edge of the planet is white? Like,
Yes.
very question.
Yes, exactly. So can I use maybe yeah. So the idea is that in this region there is a smooth mapping between initial conditions and final outcome states. So as we move the phase in this region, or as we move the inclination in this direction, we basically get always the same outcome, and there is really a smooth mapping between final outcomes. And in particular, there is a smooth mapping between phase and inclination, which of course I don't know, and final energy of the single that escapes. So here the single escapes. So he has, let's say, it gets a kind of positive energy, it gets positive energy. So here the system breaks down. But then, as I go into this direction, the energy gets lower and lower and lower until it finally reaches it goes below the escape energy. So the energy becomes negative. So here, the single is going to come back, but it's going to be also barely bound, which means it takes an infinite amount of time to come back in principle. Of course, astrophysically, maybe this single might have a apocenter of 1,000 parsecs, megaparsecs if you want. There is no limit, of course, as long as we are in isolation. And if I were to zoom in this region, I could find an infinite amount of configuration for which the single, after the first interaction, it takes an arbitrarily large amount to come back and resume. So that's why regular regions are always bordered by these extremely long lifetimes.
The total energy is negative.
The total energy is always negative, yes. But yeah, the energy of the single that escapes is negative, and here, at least for the first interaction, and here it just becomes barely bound in a smooth way. That's because it's not chaotic. You just change slightly your initial phase. Yeah. Of course, when this comes back and it has as another interaction, it might become more chaotic, maybe, yeah. But yeah, we also have to have some constraints on how long we want to integrate the system. And if we take all these interactions and we compare, for example, what is the probability for a particle of a given mass to escape, and we compare it with the theory, we're going to be surprised. So here, the masses are slightly unequal. So it's a bit more unintuitive to know what to expect. But if we take a statistical escape theory, like a recent one that was produced by Fractal, collaborator of mine, you see you should have like 56%, 28%, and 16% of the smallest to the highest mass escaper. And if we take all the numerical experiments, is not what we observe. But if we remove all these regular interactions, so these regular islands, well, the obtain is something that is much better. It matches quite well the predictions. And it's even easier to show when we have equal masses. So if we have equal masses, statistical theory and even basic common sense tells you should have 1/3 chance for each particle to escape. There is a complete mass symmetry. Well, if I were to do the experiment, and of course I have done it, and I would see that there is only 40% chance, 30% chance, and 30% chance. So things becomes extremely unexpected. They start to defy the expectation of statistical escape theory.
Why doesn't Cole's prediction capture or, take into account these ones that where the outer one just gains energy and keeps going? Why isn't that?
Sorry.
Okay, Cole's got his prediction and he's got some analysis.
Yes, Barak.
Why doesn't the analysis pick up on these ones that just scatter past and gain energy? The black one.
The black ones. Yeah, it's because the theory is still based on kind of ergodic assumption. And the idea is that your system explores different part of the phase space, but those black interactions don't have any time. Those very prompt interactions don't have any time to explore.
Yeah. Okay.
Yeah. Its theory kind of avoids it in another way, in the sense we have a chaotic absorptivity that tells you how chaotic is an interaction, but it's a bit of a band-aid in the sense it's a known function. So we don't actually know. You cannot predict if an interaction is chaotic or not a priori. So it's a bit of something that we can numerically infer only.
But for reception are too short, so you don't have enough time to mix.
Yeah.
No, I understand that, and actually the phase was.
Yeah, and again, the theory let's say, excludes regular interaction, but cannot predict them. That's the point. And you can also see in outcome properties, for example, not just escape probability. If you take the eccentricity distribution of the binaries that survive, all binaries survive technically, but you see that you should expect something that is like this dotted line here, for mostly every regardless of which particle escapes, you should see the same roughly thermal distribution in eccentricities. And while if you take all the simulation, you see you have a much super thermal distribution, which means it's much higher, much picked up one. And again, this is something that defies its odds with statistical escape theories. But we could say, okay, well, in this configuration, we have 50% interactions that are regular. Let's say to see but once we exclude this, maybe things are totally fine if we just take this sea of chaos. And to see if it's really a sea of chaos, I started to take some zooms in this phase space. And what you see from left to right and from top to bottom is this series of zoom in by 5 times 25 times zoom each in this phase space. And you see the emergence of structure. There is no real sea of chaos, a zone in the phase space where all the interactions are completely chaotic. There is a uniform color because there is no structure at all in the phase space. What you see is that as we zoom in, we keep seeing the same kind of regular structures. In this case, there are these kind of strips, regular strips. And we see them also of course, if we just measure the lifetime of the system, we see the same exact correlation that we've seen in the big plot there. So we still have, even in what looks like a completely chaotic region, we still have the emergence of fine-grained structures and fine-grained regularity in this phase space. And this tells us that, indeed, these regular regions are present at all scales. And indeed, it's a feature of chaos. And it's very well known that chaos is fractal in nature. And by fractal, to actually be more quantitative in this, to say that this is a fractal structure, we can actually measure what is the fractal dimension of our three-body problem. And the fractal dimension is a way to quantify, let's say, the filling factor of fractal surfaces in their embedded phase space. So, for example, the Cantor set is one of the simplest fractals that you can think of. You take the line segment, you take the middle, the open middle set, you remove it, and then you take the other two segments. You also remove the middle one. And eventually, the Cantor set is the set of points that, of all the points we haven't removed. And it can be shown that it is finite. I mean, actually is uncountable, but this has a dimension which is less than 1. So the embedded space, of course, is one-dimensional, but it's what we call the Hausdorff dimension is less than 1. So it's a non-integer number, which is an indication of chaos, of fractal nature. And a way to measure this fractal dimension is to, for example, box counting technique. Unfortunately, I only found this kind of example is very well known, is how to measure the coast of Britain, and you take some boxes to cover the coast of Britain, but unfortunately, well, we're in Australia, so I had to make myself the one for Australia. Okay, this is much better. And the idea is that if you take these boxes of length epsilon and you cover your coastlines, and then you make the boxes smaller, you also count how many boxes you have to take for covering the entire coastline. And then you take this limit, so the logarithm of the counting these boxes divided by the logarithm of the 1 over the side of the squares. This should tend to what is called the box dimension of this fractal set, of this set of points. And if the set is a smooth space, which you should see an integer dimension. For example, if the coast was a simple line, of course, if you halven the length of the boxes, you also double the number of the counts of the double the number of boxes you need to cover it. So you would see something a fractal dimension that is actually 1. But in the case of the three-body problem, the box dimension is not very efficient, it's not very helpful, because it assumes that we can do this limit. This limit, of course, it works if we have a infinite zoom-ins, but we don't have. We're limited by resolution, and so what I had to do is to use another kind of way to measure the fractal dimension of a set of points, which is called the 2-point correlation fractal dimension. So instead of counting the boxes, we count the number of pairs that are below a certain length. And then, so for example, on the y-axis, this is the logarithm of the number of pairs below, which are distance below a certain length scale. And this power law should amount to our fractal dimension. And if I take all the points, for example, in a zoom in, we should see this to be equal to 2. This is not exactly 2, so in the gray line, because we have some clustering due to pseudo-random number generation, which still prevents it to be completely smooth. But if we only take the regular interactions in the phase space you have seen earlier, we see that definitely this is less than 1, less than 2, less than the embedded phase space, and it's greater than 1 also as well. So it's not a completely linear feature or one-dimensional feature. And if we do if we observe this fractal dimension for all the zoom-ins, we can see that every zoom-in has a different fractal dimension, which again is telling you this is not like the Cantor set or a kind of mathematical idealized set of points. This is a multifractal, and I would expect if I were to zoom in a different phase, in a different region of the space, I would find different fractal index as well. So, and yeah, and this zoom in as well. This presupposes that we are able to zoom and measure the difference between two different initial configurations with arbitrary accuracy. And again, this is not, as I told you earlier, what I use is like numerical approximation to a solution, right? And this depends on how accurate it is our integration. And a good way to verify how important is the accuracy in this kind of experiments is to use an arbitrary precision code and compare it with my own code. So my own code is this is the last zoom in, the smallest zoom in I did in this exercise. And I use my own code, which is a tolerance accuracy, let's say, of 10 to the minus 13. And on the bottom is a Brutus code, which is an arbitrary precision, arbitrary word length integrator. So you can add as many bytes as you want, and you can increase your tolerance, decrease your tolerance as much as you want. And it can be as accurate as you want, as long as you have time to wait for the integration to happen. And you see, what happens when we have numerical errors? Our phase space starts to become fuzzy, and what were regular strips, they start to mix into the phase space. And we have what I call numerical chaos. And so numerical errors enhance the mixing in the phase space, but they do not affect ensemble statistics. So if I count the number of red dots in the top panel and the bottom panel, basically they have the same kind of outcome fraction, so but to 1%, which is extremely powerful. It tells you don't have to be extremely precise in to model in your integration, as long as you have enough number of ensembles or large enough number of realization. Maybe your individual realization is going to be wrong, so the outcome of this particular interaction maybe is wrong compared to the real approximate solution, the best approximate solution. But statistically, they are indistinguishable.
Why the red and green strips shifted?
It's a trick of the eye, because this is slanted. So your eye tries to connect them. Yeah. So okay, and yes, and of course, if we keep zooming in, and I cannot use my code, I have to use arbitrary precision code, we can actually reach a scale in separation, in perturbations, or say the distance in positions between the binary between these two pixels is less than a Planck length, if we were to assume that these are stellar mass black holes interacting. And this is a way to show that indeed chaos has no scale. And it's a way to couple as well. We can imagine if you believe in, let's say, spontaneous decay of the wave function in quantum perturbation, this is a way you can couple microscopic perturbation to macroscopic outcomes in the three-body problem, for example. Okay. I haven't shown you how actually to predict the regular interaction. So at the moment, what we can do is just exclude everything that is not chaotic and compare it with statistical escape theories. The idea the best would be actually have a way to predict these regular interactions. And I visited Douglas Heggie, who is a very famous dynamicist they worked on evolution of binaries in the 70s. Try to make an impulsive approximation to predict these regular regions, but fortunately we are not there yet. So this is basically the delta, the relative difference in energy that you are supposed to receive when you have a prompt interaction. And ideally we should be able to reproduce these large islands where the binary breaks, and there are 4 islands where basically the binary breaks immediately and the single never comes back. But unfortunately, we only find 2. So there is still something we don't fully understand, and we would like to improve, of course. Okay, so this is the summary so far. What time do I have? How much time? Yeah. Perfect. Yeah, this is not the end. So far, I've showed you that the three-body problem is both chaotic and regular. The regular part prevents us to fully use statistical escape theories to predict its outcomes. This mixing of regular and chaotic regions is really permanent until it's at every scales and allows to couple microscopic and macroscopic processes. It's a multifractal, and numerical errors introduce spurious chaos or numerical chaos, which make individual realization wrong but conserve ensemble statistics. I still don't know where to submit this paper because it's not really astronomy, it's not even physics, it's not quite math. So in any case, I can always submit it to art exhibitions, and yeah, I'm very. It's actually got selected for a traveling art exhibition in Japan now, so I'm very happy. And yeah, the last topic, briefly mentioned, is going to be related to this boundary between hierarchical triples and non-hierarchical triples. So this is again quite an old problem, and if you want, we can state it like this: how far we can put the moon from the Earth before it kind of flies off and becomes a planet. And it's not an easy problem. Because so first of all, what is a hierarchical triple system? It's a binary. You have two bound objects, and this binary is orbited by another tertiary body there. And Yevgeny has worked a great deal on these hierarchical triples and knows very well that as long as there is sufficient separation between the inner binary and the tertiary object, you can basically ignore strong gravitational interactions. And the only thing that happens, if you ignore all other physical processes like stellar evolution, this triple system evolves via exchange of angular momentum. And this causes what they are called Coséide oscillations, yeah? Where you have the inclination of this binary. Yeah, if there is a mutual inclination between the inner and the outer binary and the outer object, you can have this oscillation in the inner binary inner binary eccentricity. And these are very important for astrophysical phenomena, because if you have a very large eccentricity, this is 1 minus the eccentricity, you can have very short pericenter passages. So you can merge normal stars if they have collisions. You can have collisions between normal stars, or you can have the emission of gravitational wave radiation if this triple is made of compact objects. And probably you can better see here, this is the evolution of a triple system using, which is very well separated. On the top you have one minus the eccentricity, here you have the inclination, here you have the same major axis. And this is a triple system made of compact objects, of black holes. And the initial separation of the inner binary is 1 AU. And you know, this is a tensor mass 1 AU separation binary. Would never merge within the edge of the universe. So if we were just sitting somewhere in the universe, we would have no chance to observe it. But this binary is not isolated. There is a tertiary body on an inclined orbit. It triggers oscillations in the eccentricity. And so at each pericenter passage, this binary loses a bit of energy to gravitational wave radiation. And finally, after only 25 million years, emerges. So this is a very powerful way to create gravitational wave sources and progenitors. Okay, yes. But what happens if the separation is not enough? Okay, what happens is the triple breaks. We go from a hierarchical triple to a non-hierarchical triple. And the things happens very quickly and very unexpectedly. So this is a triple system in which the separation or the period ratio between the inner and outer orbit are not that much. You see, initially it's like this is like 2, actually 0.2, and this is like let's say the period ratio must be like about 15. And there is energy exchange, not just angular momentum exchange, also energy exchange between the inner and the outer binaries. So the period starts to change because there is energy. And you can see it's there. Same major axis of the outer binary keeps changing and oscillating. Also, the eccentricity does something very, very weird that is not really predicted by Kosály equations. And suddenly, you cannot expect when you don't know when this happens. Suddenly, the outer binary, I think the tertiary body goes into the binary, and they break up. It breaks the inner binary. And this problem is difficult to solve because yes, one can do this integration, and of course then we know the disruption time of this triple is this one. But how do we know if a triple is stable from the initial conditions? How do we know how long it will take for it to break? So, okay, so one way to do it is to so one way that I try to solve this problem, and of course Rosemary has worked a great deal on this problem from the analytical point of view as well, is to use machine learning. So what we did is to create a large data set of stable and unstable triples and feed this to a convolutional neural network. And we know if a triple is stable or not because we have it integrated. And so we can do supervised learning. And we feed the convolutional neural network with a time series of the orbital evolution, of Keplerian elements evolution of this triple system. And for example, this is what the CNN sees. It's like a time series. These are all different channels that are fed to the CNN, which relate to the orbital elements. And when this is stable and this is unstable, and the CNN learns how to predict this only based on the very early evolution of this triple. So only, let's say, a few 10 to the 5 inner orbital periods. But of course, we have integrated this system up to 10 to the 8 orbital periods, and we know if it broke at this point in time. So the CNN learns how to predict, given the early evolution of a triple system, what are the next 200 times this early evolution. So it becomes 200 times more computationally efficient than just using pure embodied integration. And this is like the usual true positive rate versus the positive rate of our different models. And eventually, we showed that they are quite good, surprisingly. We were not really expecting to work it that well. And of course, we can also use this CNN to find out which parameters are best, they best describe, they're more predictive in terms of stability of triple systems. And for example, we found that apsidal precession, apsidal lines are completely not very helpful. Same major axis ratio is better than giving the same major axis alone, and so on. So we can also use to gain some physical insights rather than just use, brute force prediction. Okay, this is the conclusion. So, okay, of course there are many more applications of the Triboli problem to astrophysical scenarios. I won't really enter into any detail. I really wanted to keep this as astrophysics free. But of course, I've been working a lot on these topics, also with Evgeny. And yeah, I hope I convinced you that it's still quite of an exciting topic, and still relevant to modern astrophysics. And yeah, thank you for listening. I'm happy to take any questions.
How can your machine learning be predictive if it is chaotic?
Yes, that's a very good question. Yes, so it's technically is hybrid between embodied. So we take a system, we evolve it. So the system is chaotic, and so if maybe we change the initial position, it's gonna change. The evolution is gonna change, but the early evolution could already display sign of chaos. So if, for example, two solutions have very different early evolution, then machine learning knows how to pick up on this. While, for example, this wouldn't be true if you only take the, let's say, initial, say, major axis, initial inclination, initial orbital properties, because then these initial properties corresponds to several different, actually an ensemble of final states due to the existence of chaos. Maybe, yeah.
Well, I guess another way to ask it is, what are you predicting?
Yeah, only 0 and 1. So is it stable or not?
Oh, stability.
Stability, yeah, just stability. Is it stable or not? We don't predict the time when this breaks.
Yeah.
But for example, if we take analytic criteria, which of course they're more even more computationally efficient, and you know, for example, given eccentricity, say major axis, and inclination, and masses, of course, you can say is it stable or not. But then you have another plethora of variables like abscidal angles, longitude of the extending node, individual phases. This is all gonna affect the evolution because the system is chaotic. So actually, given this, analytic criteria will never be able to be fully.
Close though.
Can be very close, of course.
I mean,
Of course.
You know, that's what I've done.
Of course. I agree it can be really close, but this is a way to kind of go around this and at least, given the early evolution of this specific configuration, we can say is it stable or not. Yeah.
So my, well, first of all, comment. So this idea of being ergodic, the idea of being ergodic
Yes.
is, well, first of all, you were looking at non-hierarchical, so you're shooting in a thing that had 0 velocity to start with.
Yeah.
Into a circular binary, so
Yeah.
it's super contrived.
Yeah.
And in particular, if you were mapping out the chaos boundary, like you talked about the second part, this kind of system would be deep inside, way away from the boundary. Okay?
Yeah, exactly.
So it's actually reasonable to imagine that such a system is ergodic in the sense that all the degrees of freedom are, in some sense, chaotic. But if you cut close to the boundary, it's not true that it's ergodic, and in fact you can show that if you work out the Lyapunov exponents for the whole system, not just the largest thing, right? You get the set of Lyapunov exponents for the n degree of freedom set DEs. You will find right near the boundary that only one of the Lyapunov exponents is positive.
Associated.
And in fact, in some sense, you've lost 1 degree of freedom. Not lost, but you know, I mean, 1 degree of freedom is chaotic, or in some sense. And the deeper you further away from the boundary into the chaos region, the more degrees of freedom you lose until you're at a place where you've lost all of them and you truly ergodic. But the idea of ergodicity doesn't work near the chaos boundary. That's
okay.
You know, so that's something. And just a quick question: all this lovely fractal analysis is beautiful.
Yeah.
And artistic.
Thank you.
Worthy. But is there a practical reason to care about whether this is a red dot and that's a blue dot? So, you know, like for the, you know, physical problems that we studied.
Practical.
Care about that.
Well, we care. So, is it specific to the fractal and the zoom in?
Who cares if it's fractal?
Yeah, I think it's practical. So, in the context of comparing statistical escape theories to embodied simulations, because we want to know when we can actually have a functioning predictive theory, and then of course we can use this to predict astrophysical gravitational waves. I would say maybe you don't have to zoom in and explore all the phase space. You can just remove the big island and probably you're good.
Really interesting. This is the kind of thing
Yeah, this is
to get buried in.
yeah. From practical point of view is, so for example, this is like how you measure how uniform are their interactions. Basically just
No, that's good. The large scale structure.
yeah. You still have small ones here, but the main part is, of course, resides into this. And about the degrees of freedom, I also say, okay, this is a very specific configuration. They're at rest. I also try to add impact velocity and so impact parameter, and I did find something very, very similar. Like when I had non-zero velocity plus an impact parameter, I would see this is again a similar phase space, and there is still very low resolution, but you can see some kind of regular structures. Yeah.
Gravity thing is what I was talking about.
Yeah.
You need to be far
From stability, yes. But I think some system can still cross the boundary and go this. I think that some system can.
Yeah, you do something about. But that is a horror. That's cool. Very different.
It's a metastable. I mean, by definition. Sorry.
This is very different to the configuration that we were studying.
Yeah. It is.
In actually this kind of simulation, does the sort of chaos that you're seeing emerge here, does that also happen if you reduce the masses of your body? Like if they're more like one solar mass, not?
Yep. Yeah. It's present with all masses, and
The answer is it depends on the mass
ratio. If we go very low mass ratio, then we would see that it's basically a test particle moving in the background potential of two other particles, and then of course these two other particles is not chaotic, but the third particle it is.
But her question was if you reduce the absolute masses.
Oh yes, this is complicated. Yeah.
The mass ratios, it's identical.
Yeah.
And the length ratios, identical behavior for Newtonian.
Yeah, so it gets very tricky. Actually, all the statistical theory, they break down when you go to very low mass ratios. We haven't really explored so far but basically the prediction at some point, they won't match anymore the numerical experiments, exactly because you have the emergence of very different processes. So let's say the most massive particle is also very difficult, has a greater momentum, so it cannot really get too much chaotic anymore.
If you replace 12.5 by 1 and 15 by 15 divided by 12.5, it would be identical.
Yes, if we would just rescale the masses, yes.
Down at peanut masses.
Yeah.
Get the mass ratio.
Yeah, no, you're right. Yeah. Yes, it's the mass ratio. Yeah, if you were to rescale them and make them all 12.5 Jupiter masses instead of solar masses, they would be exactly the same.
Even if you kept the same length scale.
Yeah.
Not scaled the length.
Oh, you can even scale the length. Yeah.
No, but if you give them the same lengths, it'd still be the same. It's amazing.
Yeah.
It's counterintuitive, but it's,
If you change also the length, then you can simply rescale the time.
exactly. The time gets scaled.
Yeah. The other thing which is counterintuitive to me at least is that if you take one of the masses to be like very small, you'll be in some kind of test particle limit. So I would think it will be actually simpler problem to solve because at least you maybe have like one orbit which is unperturbed basically. Yeah. So why does it break down and kind of harder people?
Because I think it's the ergodicity. I think maybe this is a good idea. Maybe you can because you're sampling the whole phase space, but maybe at some point, if your binary because it's too massive and is really not remains the same, then you should only include you should only sample the phase space associated to the test mass and not the binary. Maybe.